So this is about dynamic non-monetary markets to which objects and unit demand agents arrive over time. Um, think about problems like allocation of public housing. In the US, more than 1.6 million families are waiting on wait lists to be assigned to public or affordable houses. In refugee resettlements, there are thousands of refugees waiting in camps to be assigned to cities or locations that are willing to host them. And this happens over time. And also in organ allocation, in the US, for example, there are more than 100,000 patients waiting for deceased donor kidneys on wait lists. So they are waiting on wait lists to be allocated deceased donor kidneys. And a common problem that occurs in these situations is how to optimally trade off lower waiting times against making better matches. So that means lower waiting times against making higher quality matches. To put this problem in more context, let me focus on one of these settings and tell you more about this trade-off in that setting. And so we'll, for a couple of minutes, focus on allocation of deceased donor organs in the US. So as I said earlier, there are about 100,000 patients waiting on wait lists. For deceased donor kidneys, only about 20,000 such kidneys become available each year. So there's a huge imbalance between demand and supply. These kidneys are allocated when become available. They're allocated by a priority-based waitlist mechanism. So what does that mean? That means that agents, the patients waiting on the waitlist, are assigned priority scores based on several factors. For example, their waiting time, being a prior donor, age, medical history, and other factors. When a kidney arrives, the patient with the highest priority score is offered the kidney. If she takes it, that's great. Otherwise, we move on to the next patient, and so on until somebody takes the offer. And here is an interesting fact about the patients waiting on the list. Although there is extreme imbalance between demand and supply, these patients strategically wait for receiving higher quality organs. So some of them might decline some offers, hoping that future offers might be better. And there is heterogeneity in willingness to wait. Some patients, such as younger patients, may be willing to wait longer amounts of time for receiving offers, for receiving higher quality offers. And what does quality mean in this context? So let me be a bit more precise. There is a standard notion of quality. It's called Kidney Donor Profile Index in the context of deceased donor organs in the US. So this is a number between 0 to 100, and lower numbers mean higher quality. Let me show you a graph that plots KDPI as a plots the waiting time of patients as a function of KDPI quality. So here are higher quality kidneys, and you see that the waiting for getting a higher quality kidney is longer. So if you want a higher quality kidney, you have to wait more. Basically, it means that the waiting times are essentially prices, and the price for receiving a higher quality kidney is higher. So this is what the plot shows. Any questions about this? About this graph? Okay. But waiting is costly. Patients who go under dialysis patients who wait go under dialysis, which is a costly process and painful. And also some of them might become too sick to receive a transplant. And the point is that these waiting times can change. They depend on the allocation mechanism. If we use some other allocation mechanism, the graph that we are going to see here, this red line, is going to change. And to demonstrate this in a simple way, think about a really extreme mechanism that assigns kidneys to patients, just irrespective of quality, irrespective of kidney quality. Then this red line will just become a flat line. At least for kidneys of the same blood type, this red line will be flat line. It wouldn't depend on quality. And the key question we are going to focus on this talk is centered around this trade-off, how to optimally trade off waiting times against allocative efficiency. So how can we optimally trade off having lower waiting times against making better matches, against assigning kidneys with higher quality to people who have higher preference for quality. And not just in the context of deceased donor kidneys, but also more generally in the context of markets that I talked about earlier, like markets where unit demand agents wait on one side, objects arrive on the other side, and agents wait to be assigned to these objects over time. And before I tell you about what we do and become more precise about the model, let me just quickly tell you what others have done about these type of problems. So problems like this have been studied in the literature, and the literature can be roughly broken into two categories. The first category, optimize over general classes of mechanisms, allocation mechanisms, but they make an assumption that preferences are observable. Agents' preferences are observable. The second group dismiss the observability assumption, but on the other hand, optimize over special classes of mechanisms. And what we do basically is relaxing both limitations. You're going to assume that agents' preferences are unobservable, and you're going to optimize over the entire class of direct revelation mechanisms. And the type of questions that we will answer is, in the optimal solution, in the optimal second best, who waits how long and gets what? What is a simple way to implement the optimal solution in practice? And finally, in the last part, you're going to do some comparative statics about optimal solutions, how optimal policies change with the planner's preferences that we are going to define soon. Okay, if there are no questions, I will, in a few seconds, dive into the model and we'll be more precise. Okay. So in the model, there are agents and objects, right? Agents arrive to a pool with a flow rate of n, which we assume it's larger than 1. It's just a normalization. And agents have types. Type of an agent V is distributed according to a CDF distribution, which we call G. Objects, on the other hand, arrive with a flow rate of 1. So the idea is that there are more agents than objects. And objects have qualities, which we suppose belong to a set Q1 to QM. And these are distributed according to some CDFF. In addition to these, we also assume there's an object Q0 that has lowest quality and is in abundant supply. So you can think of this Q0 as an outside option that agents can claim at any time without waiting. There is a utility function, U of V and Q. So if the type of agent is V and the object quality is Q, UVQ gives the utility of the agent from having the object. In this talk, we mainly consider, for simplicity and presentation, we consider the case where this utility function is multiplicatively separable. So UVQ is equal to V times Q. In the paper, we relax this and consider supermodular utility functions that are useful in scenarios, for example, where agents can take endogenous costly actions. Suppose that after observing the waitlist rules, I see that I need a roommate, and this is an endogenous action that can change my valuation V. And so in these scenarios, we show that basically the extension where U is supermodular is going to be useful. But again, for this talk, for simplicity, I'm going to focus on the multiplicatively separable case to keep it simple. So there is a function CT, which gives the cost of waiting to units of time. This function is assumed to be homogeneous for all agents. Again, in the paper, we look at extensions where this can be heterogeneous, but to keep it simple throughout the talk, we are going to make this assumption. Happy to answer any questions about the cases where this function can be heterogeneous. So the assumptions we make on the cost function is that it's continuous, strictly increasing, and waiting 0 units of time has no cost. The payoff of an agent is her utility minus her waiting cost. So this function U minus how much the agent has waited, C becomes given by C, becomes her payoff. And now we define the planner's objectives. So there are 2 main objectives that the planner focuses on. The first one, we call welfare or social welfare, is the average of agents' payoffs. In the talk, we consider a case of simple average to keep things simple again, but in principle, pretty much all of the results extend to weighted average as well. In the second objective is efficiency, which is the average of agents' utilities. So basically, the idea is that efficiency only takes into account who gets what and is maximized with a positive assortative assignment, with the assignment that in which agents with highest valuations for quality get the highest quality objects. Welfare, on the other hand, is not just about that. It also takes waiting times into account. And we are going to see that the planner's objective is basically going to be a convex, a weighted sum of these 2. Any questions before I move forward to defining mechanisms? Okay. So the valuation of an agent, her type, is her private information. So we take a mechanism design approach. A mechanism elicits an agent type upon arrival and assigns her an allocation plan. What's an allocation plan? It's just the joint probability distribution over the time of allocation and the type of object that the agent gets allocated. So to give an example, it looks something like with probability half, a month from now, you're going to get an object of quality 15. If that doesn't happen, with probability 1/3, 2 months from now, you're going to get an object of quality 20, and so on. And so the type of mechanisms that we focus on elicit agents types and promise them such allocation plans. In addition, we are going to work with mechanisms that satisfy 3 common assumptions. The first one is incentive compatibility, which means that these agents provide the right incentives for agents to report their type truthfully. Second one, individual rationality, and the third one, steady stateness. Let me go over these one by one. Right. So incentive compatibility, as I said, means that an agent's payoff is maximized when she reports her type truthfully to the mechanism. Individual rationality means that the payoff of an agent of type V from participation in the mechanism is at least her payoff when she immediately claims her outside option, Q0. And the steady state assumption just says that there is time, however, the composition of the pool remains the same across time. So if you take a snapshot of the market at any time, the snapshot shouldn't change. And why is this a reasonable assumption in this setting? So I am giving you first a mean field model, right? When there are continuums of agents and objects arrive to the pool. Later on, at the end of the talk, we are going to look at a model where agents and objects arrive according to Poisson processes. So there will be discrete, there will be a discrete market. there, the steady state assumption we make is just the usual one in stochastic processes. It's the existence of a steady state distribution. But what we observe there is that as the arrival rate of agents and objects in these Poisson processes are scaled and become larger at the same rate, then stochastic deviations, fluctuations from the average case, happen with smaller and smaller probability. So the limits when both sides go to infinity is basically the mean field model, in which these fluctuations happen with probability 0. So basically, this assumption that the composition of pool remains the same across time is just a translation of the usual stochastic, usual steady state assumption in stochastic processes when the market becomes large in a continuum. So so basically, this is the definition of mechanisms that we focus on. And next, I'm gonna tell you the planner's objective. But before I proceed, any questions about definitions for mechanisms? Okay. So the planner's objective is just a weighted sum of allocative efficiency and welfare. So there are these two parameters, lambda E, this is the coefficient for efficiency, and lambda W, the coefficient for welfare. If lambda W is 0, then the optimal thing to do will be a positive assortative assignment. But in general, we are interested to know what is the optimal mechanism for general welfare rates. Okay, so what's an optimal mechanism? It's just an incentive compatible, individually rational, and steady state mechanism that maximizes this objective. So this is the first question we are going to look at. Which mechanisms are optimal? And here is basically the first result. First, to give you that result, I need to define a class of mechanisms that contain the optimal mechanism. And to define these mechanisms, rather than giving you allocation plans, which is a rather abstract object, I'm gonna define them in terms of queue-based mechanisms. So these queue-based mechanisms basically produce the same allocation plans, except that they do that in the context of queues, which is a more they do that implicitly in the context of queues, which is a more intuitive object to understand. Okay, so this is a class of mechanisms that we call monotone disjoint queue mechanisms. And in these mechanisms, there are a finite number of queues. In the example I'm showing in the picture, there are 3 queues. The objects are partitioned to the same number of queues. So, and here there are 3 intervals. And these partitions are monotonic. So these are basically intervals. And the top interval is sent to the top queue. The middle interval is sent to the middle queue, and so on. Okay, so intervals are sent to queues in the order. And then, so this is how objects are assigned to queues. What about agents? So agents, when they arrive, they compute, the planner computes for the agents the payoff the expected payoff they will achieve from joining each of the queues, and assigns each agent to the queue that maximizes her expected payoff. So this is done to ensure incentive compatibility will hold. So I've told you how agents and objects are assigned to each queue. I haven't told you yet how objects are assigned to agents within each queue. So, and that's something that's just simply done using a FIFO policy. So when agents are sent to a queue, they wait in the queue, and assignment of objects to the agents in that queue is just first in, first out. So they wait, and whenever it's each object that is sent to that queue is assigned to the agents with the longest waiting time. When an agent gets an object, they cannot decline it. They just accept the objects and leave the queue. So this is a queue-based mechanism. One thing that I need to tell you to finish the definition is waiting time. What is the waiting time in each queue? Well, the waiting time in each queue will be set by the queue length. Right? And these queue lengths are actually can be set by the planner, as long as the inflow of agents to a queue is equal to the inflow of objects to that queue. These queue lengths will be maintained at a steady state. And this completes the definition of the mechanism. And the theorem is that there is a monotone disjoint queue mechanism. There is a mechanism of this type that I just told you that is optimal. So if you choose the number of queues and the intervals that send the objects to queues carefully, then the mechanism will achieve the optimal second best. One thing is noteworthy about the length of these queues. So the length of these queues will be, if you think about an indirect implementation of the optimal mechanism, where agents arrive, they pick a queue to join. There is no planner involved to elicit the agent's types. So in such an implementation, you can think about endogenous waiting times in the system. And there will be basically a unique number of queue lengths, one for each queue, such that the whole system can work at a steady state. So the mechanism is it's possible to every such mechanism will be pinned down entirely by just the partitions of the objects that are sent to the queues and the number of the queues. Okay, so this is the basically first result about how optimal mechanisms look like. Any questions so far? So a quick discussion of optimal mechanisms and then an example. First, so we can view these waiting times as prices. And for any queue structure, these prices are set so that the market is cleared, meaning that the number of agents who demand to join that queue will be equal to the number of objects sent to that queue. Sortative mechanisms that send each object type to a distinct queue are not always optimal. And the reason is that think of agents with really high types. For such agents are willing to wait very long amounts of times for quality. They derive the waiting time for these objects very high, above the socially optimal level. And what happens in the optimal mechanism is that by pooling object types, like we see in the picture, the waiting times become lower, and the optimal mechanism does this in a way that the loss from misallocation by pooling and the gains from reduced waiting times is traded off in an optimal. Okay, I see a message. What is the optimal behavior of agents in the indirect mechanism? So do they know the length of each queue before selecting the queue to join? Very good. Yes. So then basically they know the length of queues, or you can think of it, they know the expected waiting time in each queue. That's all they need to know. So after observing the expected waiting times and the expected object type that they will receive from waiting in each queue, they are able to compute their payoff from joining each queue. And then the way they join these queues is that because of supermodularity, higher type agents join the higher queue, join the higher queues, basically. So there is a positive assortative assignment across queues, but within each queue, there is some pooling. The assignment is not positive assortative. Other questions? Okay. Yeah, so I'll tell you more about this in the proof outline, and also about how these intervals should be chosen. But let's see an example. Why is pooling necessary at all? So in this simple example, agents arrive at rate of 1. Types are drawn from the uniform distribution over the unit interval. There are 2 object types, 1 and 2. We assume that each object type arrives at a rate of 1. So let me be more precise. Objects arrive at a rate of 1. So in this market, the arrival rate of agents and objects are equal. Qualities of the objects are drawn from the uniform distribution over the set that contains 1 and 2. So there are high quality objects and there are low quality objects. And there is not enough high quality objects for everyone. The utility function is multiplicatively separable. And we are going to focus on a family of mechanisms. And I'm going to give you a queue-based description of this family. So there are 2 objects shown here. Agents are shown on the left side of the picture. So from lower type to higher types. There are these mechanisms, this family of mechanisms contains 2 queues. And the way they work is that at rate 1 minus epsilon, higher type objects are sent to the higher queue. The remaining fraction of higher type objects at rate epsilon are sent to the bottom queue. And it's the opposite for low type objects. Fraction epsilon of them are sent to the top queue. Fraction 1 minus epsilon of them are sent to the bottom queue. And the rough idea here is that by changing epsilon, we can change the amount of pooling in the mechanism. So in this mechanism, agents with type above half are sent to the top queue. So higher type agents that half of the agents, higher type agents are sent to the top queue. And like I said earlier, at epsilon equals 0, we will see no pooling, meaning that higher type agents are sent to higher type objects, right, or higher queue, and vice versa. At epsilon equal half, we have complete pooling, meaning that, the distribution of objects sent to each queue will be identical to the other. And it means that any agent who joins either of the queues is going to receive an object uniformly at random from this set. So we will have complete pooling. To finish the description of the mechanism, I need to define a few other things. So first of all, for the mechanism to run at a steady state, the arrival rate of agents in each queue must equal to that of objects. Okay, so how do you choose the number of queues is the question. Was it an earlier question, or in this, if it's about maybe I'm seeing the question with a bit of lag, but in this example, there are just 2 queues. Yeah, let me know if that does not answer the question. So, for the mechanism to finish the description of the mechanism, we also need to define a few things, including that the mechanism satisfies the definitions.
Hello,
yes.
Afshin, can you be clear here? So if you have more than two qualities, how do you choose the number of queues? In this example, we just have 2 qualities, 2 types.
Exactly. In this example, we have 2 qualities. If you have this picture in mind.
Exactly. Why 3?
I am gonna tell you about I'm going to tell you about this more in the proof outline, how in general we can choose the number of queues. But right now, I just want to show you an example to demonstrate that some level of pooling is needed.
Okay, I see.
So that's I'm not gonna something very simple. Just why do we need pooling at all? Why it's not the case that positive assortative assignments are not in general optimal? There will be some insights that will be derived from this example, which we are gonna use later.
Okay, thanks.
Sure. Okay, so how can we ensure that for each mechanism to run at a steady state, the arrival rate of agents to each queue must equal to that of objects? So that is indeed the case because we send top half of agents to the top queue. So the arrival rate of agents and objects are going to be equal for the top queue. By symmetry, the same holds for the bottom queue. So the balance condition is satisfied. Question to finish the definition of the mechanism, a question you need to answer is, what are the queue lengths? So in other words, what are the waiting times in each queue? I know that because the allocation of objects to agents in queues are first in, first out, the waiting times are going to be equal for all agents who join the same queue. So I call this variable T2, waiting time for the top queue, and T1, waiting time for the bottom queue. And basically setting each agents who join the top queue are going to incur a waiting cost of C2. Agents who join the bottom queue are going to incur a waiting cost of C of T1. C is invertible, so we can just call C of T2 C2, we can call C of T1 T1, and we can think of the mechanism setting the waiting costs C1 and C2. And here is an assumption we are going to make in this class of mechanisms that we study. So the assumption is that C1 is equal to 0. Waiting cost of there is no cost of waiting in queues in the bottom queue. If you join that queue, you're immediately going to be allocated an object. And if you're asking why is such an assumption is reasonable to make, well, just to motivate this assumption, you can show that over the class of optimal mechanisms, this assumption must hold, meaning that if waiting cost at the bottom queue is positive, you can reduce waiting costs at both queues. You can shift them so that the waiting costs are reduced in these two queues, but the objectives of the planner will not change. So agents will join queues in the same way. It's not that the objectives of the planner will not change. The objectives of the planner will be improved because waiting times go down. So basically, if you condition an optimality of the mechanism, this is an assumption without loss of generality. So C1, waiting cost at the bottom queue is 0. And what should be the waiting cost at the top queue? What should be C2? To answer that, we are going to write the indifference condition for the agent of type half, for the middle type agent. Okay, so what does that mean? That basically means that this agent should be indifferent between joining the top queue versus joining the bottom queue. If that's the case, then all agents with higher types will join the top queue. All agents with lower type than half will join the bottom queue, and the steady state condition will be satisfied. So we need to answer how can that happen? We basically need to solve the indifference condition for agent type half. And that says the payoff of the agent from joining the bottom queue should be equal her payoff from joining the top queue. Let's just verify that these expressions are indeed the payoffs I mentioned. So here we have type of the agent, V, times the expected object type she receives from joining the bottom queue. there is no waiting time. So this just gives the payoff of any agent of type V from joining the bottom queue. The other expression on the right side is similar. So it's the type of the agent times the expected object type she will receive from joining the top queue minus her waiting cost from joining the top queue, right? Because the waiting cost could be positive. In the top queue, we're gonna include C2 here. By setting V equal half, this will give the indifference condition for the agent. Solving this will give us the equilibrium, if you may, quote unquote, equilibrium waiting cost. So C2 equal half minus epsilon should be the waiting cost at the top queue. C1 equals 0 is the waiting cost at a bottom queue. These are the waiting costs, the unique waiting costs under which this mechanism that I described in the top figure can perform at steady state. Any questions about these waiting costs? All right. So right away from these waiting costs, we can see the trade-off I have been talking about in the talk. We can see that as epsilon goes down, we can see that increasing epsilon means that efficiency goes down, right? Because there is more pooling. The assignment becomes less positive assortative. On the other hand, increasing epsilon reduces waiting costs. But we can see that from the value of C2 here. And this means there is a tension between efficiency and welfare. So what is the sweet spot? What should be the optimal value for epsilon? And to answer that, let's just plot all possible values of welfare and efficiency that we can derive from varying epsilon. Okay, so in this example with uniform distribution, what we are going to get is just a nice 45-degree line. To the left, we have one endpoint of the line, which corresponds to epsilon equal half complete pooling that results to the point with the highest welfare. To the right, we have another endpoint, epsilon equals 0, no pooling. That gives the point with the highest efficiency. And basically, the idea is that as you move up on the Pareto frontier, lower waiting times compensate for the efficiency loss. But what should be the optimal solution that the planner picks? Well, to answer this, I should mention another fact that I wouldn't prove, but we do this in the paper. So if you're curious, you can look up the proof there. But basically, this 45-degree line gives the entire Pareto frontier. So if you think about all possible direct revelation mechanisms, not just the ones I described earlier, the Pareto frontier you are going to get from them is going to be this line. And now we can answer the planner's problem. So the planner wants to maximize an objective function, lambda E times efficiency plus lambda W times welfare, with this weighted sum. And because this line is a 45-degree line, the planner's problem has a pretty simple solution. If the weight on efficiency is smaller than the weight on welfare, then the optimal way for the planner is picking the point to the left. That point is going to maximize this weighted sum. So complete pooling is going to be optimal if the planner places a higher weight on welfare than efficiency. Otherwise, if the planner places a higher weight on efficiency than welfare, then no pooling is going to be optimal. This weighted sum is going to be maximized by this point, the right point on the Pareto frontier. So in this simple example, it happens that there is basically one of these two really simple policies is always going to be optimal. either complete pooling or no pooling. Some level of pooling is going to be needed when the planner places a higher weight on welfare. Now, in general, do we need more complicated mechanisms at all? The answer is positive. For example, in this example, suppose that instead of the uniform distribution, we have a bathtub distribution, quote unquote bathtub. It's basically a distribution where the CDF looks like the PDF looks like a bathtub. And then neither of these two mechanisms are going to be optimal, neither a complete pooling nor no pooling is going to be optimal. And we are going to need more complex pooling mechanisms, which were given in the theorem that I described earlier. Okay, so in the remaining time, I'm going to quickly go over two other results that I told you about. One, implementation through waitlists, waitlists with deferrals, and the other one is comparative statics. And towards the end, we are going to get to talk a little bit about the proof. So in this mechanism, in the optimal mechanism that I told you, does not allow agents to decline their assignment, meaning that when they get to the when it's their turn, they have to take the object they are assigned. They cannot say no. Right? They have to take it and they have to leave. In practice, many waitlists allow agents to decline offers. Also, there are relatively a few number of queues. There are not too many queues. And motivated by these two observations in practice, we ask whether it's possible to implement this mechanism in a different way so that these two conditions are satisfied. We show that the answer is yes, if the planner can design the information disclosed to agents about the objects. So if this is possible, we show that the planner can implement the entire mechanism with a single queue, and agents can decline offers. So what does that mean? I'll start making this more precise. An information disclosure policy is just a set of distributions, mu q, for each object quality q. So when an object arrives, rather than disclosing the exact quality q, the planner is going to draw a signal from distribution mu q, and is going to reveal that signal to the participants instead of the actual object type. The implementation we are interested in is based on a first-come, first-served waitlist with deferrals. So I'm going to define the first-come, first-served waitlist with deferrals under an information disclosure policy. What does that mean? Let me show you using this picture. So suppose an object with quality Q arrives, then there is a disclosure policy, mu Q, and instead of disclosing the exact object type Q, the planner is going to disclose the signal drawn from mu Q. The signal is going to be offered to the first agent. If she says no, we go on to the next agent, and so on, until somebody accepts the offer. Okay, so this is what we call first-come, first-served waitlist with deferrals under a disclosure policy. And the class of disclosure policies that we are interested in are those that pool adjacent object types. So what does that mean? It means that there is a partition of object qualities to intervals, and rather than disclosing the exact quality, the planner is going to disclose the interval that contains the quality to the agents. And here is the theorem. There is such a disclosure policy that pools adjacent object types, such that the first-come, first-served waitlist with deferrals that I described earlier under this disclosure policy is going to attain the same objective as the optimal mechanism. So what does it mean? Let me explain using this picture. Suppose an object with quality Q arrives. The planner has already chosen some intervals that partition the object qualities, And rather than disclosing Q to the participants, the planner is going to disclose the interval that contains the Q. Okay, this interval is going to be offered to the first agent. If she takes it, great. Otherwise, we move on to the next agent and so on. Okay, the theorem says that when these intervals are chosen carefully, this simple mechanism is going to attain the optimal objective over the entire class of direct revelation mechanisms. And a quick point about the proof is that these intervals can be chosen just the same way that we choose the intervals in the first theorem I told you, in monotone disjoint Q mechanisms. But the proof here is going to be different. Basically, the agents waiting in the queue here are playing a game, because the decisions of me for accepting an object depends on the decisions of those ahead of me. And what happens in the proof is basically analyzing this dynamic game and showing that it has a unique equilibrium in which the payoff, in which the planar objective is identical to the planar objective under the optimal mechanism. Okay. So yeah, let me tell you a little bit about comparative statics, and then if there is time, maybe a couple of minutes about how the proofs work. Okay, so the planner's objective is this weighted sum, right? Lambda E times efficiency plus lambda W times welfare. And here's the comparative statics result. Suppose, fix the weight on efficiency. Suppose that lambda E is fixed. Optimal disclosure policies become less informative as lambda W, the weight on welfare, increases. So I'll give you a few seconds to think about this. So the idea here is basically considering the first come first served waitlist with deferrals mechanism that I mentioned earlier. So that mechanism uses disclosure policies, right? And the theorem says that as the weight on welfare increases, optimal disclosure policies become less informative. So let me show this using a picture. Suppose that the weight on W is 0. Then optimal mechanisms or optimal disclosure policies do not pool object types. As lambda W increases, as the weight on welfare goes up, some level of pooling is needed. There will be these intervals that pool object types. The theorem says that as lambda W weight on welfare goes up, these intervals become coarser. They expand from both sides. They might collide at points, in which case they just get merged, become one interval, and grow together as one interval. Any questions so far about this theorem? All right. So one observation we can make from this comparative statics is from the same comparative statics is about distributional equality. Note that as the weight on welfare goes up, larger subsets of agents are pooled together in the set inclusion order. And that just means the mechanism will treat larger subsets of agents equally. So the assignment becomes more equitable in the Lorenz order. Lorenz order is a classic notion for measuring equality. I'm not gonna define it here given time, but basically the intuition is what I mentioned earlier: larger subsets of agents are pooled in the set inclusion order. So in this sense, you can think about, yeah, I'm gonna skip the definition of Lorenz order, but yeah, so this is the formal statement: fix the weight on efficiency, optimal disclosure policies become more equitable. Or more generally, you can think about it, optimal mechanisms, optimal direct revelation mechanisms become more equitable in the Lorentz order as the weight on welfare increases. So in this sense, you can think of welfare as a proxy for distributional equality. And here is a corollary of this result and a reference to one of my other papers that makes this point in broader settings, also in monetary settings. But this trade-off between welfare and this trade-off between efficiency and distributional inequality on the Pareto frontier could be proved more generally. And one of the corollaries is that the Gini index preserves the Lorentz order on the Pareto frontier. So this is not directly relevant to this talk, but yeah, you can. I'm happy to tell you more about this in more general settings after the talk. Okay, so quickly about the proof intuition for this theorem. Fix lambda E the weight on efficiency, optimal disclosure policies become less informative and more equitable as the weight on welfare increases. For the proof outline, we need to define the notion of interim allocation rules. So for a mechanism, its interim allocation rule A is just a function that gives for each agent type V the expected object type allocated to that agent. Given an interim allocation rule A, the envelope theorem just gives us readily the expected weighting times for agents of each type. So what is nice about interim allocation rules is that they basically summarize the entire mechanism. And the planner's objective, therefore, can be written as it's not an implication, it's a statement. The planner's objective can be written as a function of interim allocation rule. And it's, in fact, becomes a linear functional. The planner's objective becomes a linear functional of the interim allocation rule. So it's going to be this integral that basically consists of two parts. So one is the interim allocation rule for type V, and the other one has two summands that take into account from efficiency and welfare. Let's call this summand WV, and the planner's objective becomes maximizing this linear functional, basically. And W is something that is sometimes called a virtual value function. And what we show is that basically as the lambda W, the weight on welfare goes up, then the optimal policies become less informative. And why is that? So to tell you that, I need to tell you how to solve this optimization mechanism. And the way these optimization mechanisms are typically solved are using a procedure that Morrison called ironing. So this procedure plots the function W, as we see in the picture here, and then it irons the function W, meaning that it makes the function monotone if it is not already monotone. Using a procedure called ironing. How it's done, I am skipping that step. But what is nice about the procedure is that at the end, you can readily read the optimal solution from the outcome of the ironing procedure. In the parts of the function W that are not ironed, the optimal solution is going to be positive assortative, meaning that higher agent types are going to be assigned to higher objects. In the iron intervals, on the other hand, optimal solution is going to feature complete pooling, which means that agents in those intervals are treated identically. Two agents whose type belong to the same interval are treated identically. the result we show is a monotone comparative statics result about the ironing procedure. So we show that when the weight on welfare, when the weight on efficiency goes up, well, when the weight on efficiency goes up, this function W becomes more increasing, right? Because the coefficient of lambda E is an increasing function. The result we show is that when this happens, when the function W becomes more increasing, ironed intervals shrink from both sides. And that's basically the result we saw earlier. Interval, if the weight on efficiency goes up, intervals that pool agent types shrink from both sides. And that's the core of the result. So that means smaller subsets of agent types are pooled together, and optimal disclosure policies become more informative. So that's the proof intuition for the comparative statics result. Any questions about this? All right. So there is another result that I think I will skip over given the time out of time, but just to put it in briefly, if you're curious, you can look it up in the paper. This last result is about, are there conditions under which optimal disclosure, optimal mechanisms become very simple? And we answer positive. The condition is high imbalance. So there is one natural condition that also sometimes hold in practice. Suppose that there is a lot more agents than objects. And in these scenarios, we show that basically this flat 45 degree line that we saw earlier is going to be revived. When there is severe scarcity, we are going to get a Pareto frontier that looks like a flat 45 degree line. And it turns out from this that, again, complete pooling or no pooling, one of these two mechanisms are always going to be optimal when there is severe scarcity. So I'm basically just gonna go over the policy implications, and that will be the conclusion of the talk. So we see that there is a simple way to resolve efficiency welfare trade-offs in dynamic allocation problems. Queues, these are basically queues that pool object types together. Information design can help us simplify the structure of allocation mechanisms. So think about scenarios where quality measures such as KDPI are commonly used. So we basically, the high level finding here was that coarsening or refining these measures can effectively resolve the trade-off. Sometimes in practice, complex priority rules are used. One high-level take from this could be that if we can design these measures carefully, that will give us optimality. We won't need complex priority rules. And there could be trade-offs between welfare and informativeness. And we saw that for mechanisms that achieve higher welfare need to be less informative. And therefore, policymakers should consider inequality implications from placing higher welfare weight on allocative efficiency. The reason is that informativeness and equality are directly related. And finally, allocation of scarce resources that I talked about in the end, we see that allocation of severely scarce resources, we see that in these scenarios, that one of the two mechanisms, complete pooling or no pooling, could be optimal. There may be no middle ground. So the planner can focus on one of these two simple policies. Yeah, so I am gonna skip over the discrete markets. I'm just gonna flash the related work slide, and then I'm gonna finish leaving the conclusion slide.